Okay. Yeah, welcome everybody who has joined. So for those of you who are not in Autonomous, I'm Charles. I am the team captain for Autonomous, and we're a team of, I'm sure you probably know, but we're a team of students building an autonomous self-driving car for the SAE auto drive competition. And, we have, this is a drawing of the car you can see on screen already. And so today, as a series of 5 tech talks that are going to be happening through the rest of the term, we're gonna, give you some intro and some information on our autonomous vehicle and, how they work. So today we're gonna be talking about local planning and control, which is, I'm sure the presenters will go into more detail later, but it's essentially like the how we define how our car will move inside of the space, right? Like what path it will follow. So we have 3 presenters, Ayush, Kushant, and Steven, if you guys want to introduce yourselves.
All right, hey guys, welcome to the Local Planning and Control Tech Talk. My name is Steven from Mechatronics.
Hi, my name is Ayush, and I'm a third-year Mechatronics student again at Waterloo.
Hey, I'm Kushant. I'm a grad student at University of Waterloo.
Awesome. So in our tech talk today, we're going to talk about an overview of a stack, our local planning stack and controller, as well as our current implementations, such as feasibility guaranteed lane change and double lane change planner, local parameterized curve generator, and MPC controller. And to wrapping up our talk, we'll be showing you a demo. So here's an overall stack from a really grand perspective. We have 2 sides, one's perception, one's planning. Perception for us to use computer vision to make sense of our surrounding, and planning is the team we're on, which is navigate from source to destination while following a proper trajectory and doing a safe maneuver. So within the planning stack, there's a few things happening, and this is a really simplified version of the pipeline. So global planning is about determining a path from our source to destination. So you can think of it kind of like GPS or Google Maps. Behavior planning is about a finite state machine to determine the velocity profile and high-level decisions, so we can stay on the path while obeying traffic law and regulations. Now onto our side. So local planning is between the current vehicle's location and how we can adjust our steering wheel and speed to stay on the path. And finally, feedback control is actually calculating the steering angle and speed and sending it to the vehicle. So this is a high-level overview of what we do. So we take a path generated from behavior planning and the current vehicle information, and we output a reference path that will get us or keep us on the path that's being passed into us, as well as instructions being sent to the vehicle, the information such as steering and speed that's being sent to the vehicle. So in that sense, you can kind of think of us as like the hands and feet of the human driver that keeps the vehicle on track and at the right speed. And Kushan will talk about vehicle modeling.
So whenever we talk about vehicle modeling, we have 2 types of vehicle model that autonomous stack follows. One is kinematic modeling, which uses geometric constraints to define the motion of the vehicle. And then there is dynamic modeling, which uses all the forces and moments acting on the vehicle to define its motion. Now, dynamic vehicle model captures the vehicle actual performance more accurately, while kinematic is less accurate on that. But dynamic model is computationally expensive, being nonlinear, and requires double integration for position predictions. The advantage of using kinematic model is that it can be used for a wide range of speeds with relatively high accuracies, which make it a perfect model for our stack. Local planning. So the aim of local planning is to acquire qualitative decisions from behavior and generate a feasible collision-free and comfortable motion profile to be passed on to control layer. If planned motion has information with respect to time, when to be where, then it's referred to as trajectory. Almost all the local planners decompose motion profile into path generation and velocity profile generation. But our friend from WATO, Mohammed, came up with this unique idea of a parallel architecture of local planning and controller. Next slide. So we have different types of local planners. They are categorized into variational, graph search, or incremental search methods. Variational methods make use of calculus to find optimal motion profile, which can be done by representing search space, obstacles, and vehicle kinematic constraints, and then formulate it as a optimal control problem. Whereas graph search methods discretize the workspace of the vehicle as a graph, where the vehicle model is formulated as a finite set of vehicle states, and edges represent needed control actions to achieve those states. For example, probabilistic roadmap is example of the graph search methods. Then we have incremental search methods, where we randomly sample the control actions and incrementally generate reachable paths, which are referred to as tree for the vehicle to traverse. For example, RRT and SST and state lattice planning, rapidly exploring random trees. So for year 3 competition, we had implemented Freinet local planner with feed-forward controller. Freinet planner is an optimal trajectory generation method which uses a semi-reactive trajectory, which can be integrated with the behavioral layer. Now, everyday scenarios of driving maneuvers include merging into traffic flow, passing with oncoming traffic, changing lanes, or avoiding other vehicles. This algorithm provides for reactive obstacle avoidance by the combined usage of steering and braking acceleration. But we were facing some problems in the dynamic obstacle avoidance. Therefore, we preferred using model predictive control.
Okay, so now talking about our current stack. So our current implementation comes with two parts, a spline generator and an MPC controller. The spline generator takes the path in XY coordinates from the behavior planner, which converted to a proper quintic spline, one for the x-axis, one for the y-axis. Then the MPC controller takes in the coefficients from the spline generated by the spline generator, along with current vehicle information such as steer, speed, and location, and calculate the desired steering angle and speed, which my teammate will explain in more details. Then these information are being passed to the vehicle through the CAN bus. Some of the tools we're using include Melodic ROS Kinetic, Color Simulator, which is an open source simulator for autonomous driving, Casati, an optimization tool for non-linear optimization, and Color ROS Bridge, which is like a two-way communication tool between ROS and Carla. Now talking about controllers, just a really brief overview. There are two types of controllers available. One is open source control and the other one's closed loop control. Open loop control doesn't have feedback, doesn't care about what's going on, what's actually happening. So which means it has more chance for error. For example, a control could be like move 5 meters forward and then stop. The vehicle doesn't know that it actually moved 5 meters forward, nor does it know it stopped right away. Closed loop control takes in the feedback from the system and it tries to continuously correct it. And as a result, it minimizes the error present in the system. For example, the image to the right will be considered as a closed loop control because the vehicle is initially off track and try to compensate it by turning more aggressively inwards. Some examples of closed loop control includes MPC, Stanley, and PID. So in a nutshell, standing controller is a series of equations that we can use that takes our heading error and cross-track error to calculate for the desirable steering angle. PID controller takes the derivative, integral, and the current value of the error function and sum them together to give us a proper output. MPC controller essentially it first makes a models of vehicle kinematics with a series of equations and then optimize it. And we'll talk a bit more about MPC controller later on as well. So MPC control is referred to as moving horizon control. So it optimizes control by prediction of the future behavior of the system using the finite window or horizon on those predictions and current measured estimate of the system. Optimal control inputs with respect to defined control objectives and subjected to the system constraints are computed. So after a time interval, measurements, estimations, and computing process is repeated within a finite horizon, also known as receiving horizon control. So if you look at the image on the right-hand side, so we are predicting several possible paths that the vehicle can take, and then we try to optimize for one that has the least steering angle or the one that has that's the least jerky, and then we execute a first step for that path. So that would be an example of MPC control. Okay. And now Ayush is going to talk about the current implementations we have.
Awesome. Yeah. So next slide, please. Cool. Yeah. So let's talk about simultaneous local motion planning and path following control. So this is generally the decision-making framework that we intend to use for our stack. It's a parallel integrated architecture that generates the control actions. So the parallel part would be the local planner and the feedback planner. The feedback controller, which is gathering the data from the behavioral planner simultaneously to make decisions. So we have tested this framework using Carla. And now we attempt to integrate the system into our autonomous stack and decoupling it from Carla entirely. Okay, so more on, so the like before, actually, can you go back one slide? Right, so here you can see, the global planner feeds data into the feasibility checker, which will then determine if we will, it'll basically let us know if certain maneuvers are possible, which will then send it to the behavioral planner, which will, again, then send some points that it wants to go to the local planner and feedback control. So let's talk about more of these in the next slide. So the feasibility checker is basically a module that's responsible for two tasks, and it's basically planning any needed lane changes obtained from global planning, and it calculates the road curvature information from the entire route. The local planner handles obstacles by performing double lane change maneuvers while simultaneously generating new paths, which are represented as parametric curves. And then we have our feedback control, which is integrated. It's basically the MPC control thing that we're going to use. Yeah, it's a model predictive path following control. So more on feasibility guaranteed lane change and double lane change planners. So the proposed lane change and double lane change planners stand out against other techniques, and as the obtained maneuver is feasibility guaranteed. So which pretty much means that the obtained maneuver relies on vehicle static constraints represented by its minimum turning radius and the vehicle dynamic constraints based on its speed and maximum allowable lateral acceleration to determine the maximum admissible curvature of the road. And given the maximum curvature and the desired lateral shift, the longitudinal distance needed to perform the required maneuver is obtained, and therefore we get the mathematical equation for this maneuver. So now when I talk about lateral shift, I mean the distance from one lane to the next lane that we need to do. And longitudinal distance is pretty much the distance in front of you or behind of you. And so, yeah, so pretty much once we receive the mathematical equation of the maneuver, yeah, it's guaranteed to be feasible. And then we send it off to the behavioral planner. And yeah, and this maneuver does not require extensive computations to be calculated, so it's very useful. So this is more on the lane change planner. So this is a lane change maneuver. We use a sigmoid function for this. And you can see here that, the B value is actually the maximum lateral distance required to make the lane change. And A is the urgency of the maneuver. So you can notice that, the longitudinal distance changes as the A value changes for the same lateral shift of B. So the more urgent you are, the less longitudinal distance you would require. So here is our DLC maneuver, or the double lane change maneuver. It's basically a bell function that we use. Again, H here is the maximum distance required to avoid the obstacle that's in front of you. So that's why we would do a DLC, so that if you have an obstacle in front of you, you can make the double lane change to overtake it. And so H would be the maximum lateral distance or the maximum lateral shift, and the M would be the sharpness of the curve. And again, the M changes depending on and the longitudinal distance would change depending on your M. So the one thing that's very important for an MPC controller is having multiple splines, as we talked about earlier. So we have a online parametrized curve generator. And given the road curvature calculated offline, the global route to the target destination, and the nearest waypoint to the vehicle, the curve generator uses solves this problem using a least squares optimization and generates two quintic splines. So one is for the X direction and one would be for the Y direction. And then the road curvature information is used to determine the parametric curve length, such that the higher curvature values require smaller total length to capture the maneuvers smoothly. So again, here is just another representation of what the why the parameters, how the curve generator is generating these splines, I guess. So what we're showing here is pretty much the vehicle on the left that's faded out is where the vehicle used to be at position K-1, and the vehicle in the middle is where the vehicle is currently. So at position K-1, we generated a spline, which is represented by this green dotted line. And at the actual position K, or the current position, we generated a spline that's represented by the pink line. And so this MPC controller would look at these two splines and determine, and that's how it determines the current spline, which is PK. And as you can see, these would be overlapping curves so that they're they're smooth for motion. And so pretty much to sum it up, we have these parameterized quintic splines, and we have the double lane change maneuver, which would then result in a collision-free parameterized path. And next would be Kushant talking about feedback control.
Sure. So to interface with the vehicle actuators to execute the planned motion, we have different feedback control schemes. We can have trajectory tracking or path following. In trajectory tracking, a time-varying reference is being used to control the speed and traverse path of the vehicle. But in path following, a higher priority is assigned to error minimization between the reference path and the ego vehicle location. So speed might change to achieve better path following accuracy. However, autonomous driving requires higher priority for error minimization between reference path and the ego vehicle location rather than maintaining a strict reference speed. Therefore, the path following would suit our autonomous stack. Next slide. So here we depict a parameterized quintic spline generation where we use least square error as an objective to find quintic splines where the splines describe the motion in X and Y directions, resulting in 12 different parameters, which are again optimization variables, 6 for each equation, which are solved using a library called IPPOP, which is a NLP solver. And as we find the parameters, we have certain constraints, such as maximum curvature. The maximum curvature should allow us to plan lane change smoothly, even in case of crisp waypoints. And then we use Scala route planner to find route from an initial point to random target point. So this was the scenario of the Scala route planner, but now as we are trying to integrate it with autonomous stack, the locations will be provided passed on from the behavioral planner. Next slide. So the path following scheme integrated in decision-making system is called model predictive path following control, which treats the path parameter and determines the path evolution as an extra state, and it uses an extra virtual control input to determine the path parameter time dynamics. As you'll see in the simulation, it is denoted by act path parameter. Such a technique gives the controller an extra degree of freedom to follow the path in an optimal manner. Next slide. Therefore, the MPC feedback control loop consists of an augmented system model, vehicle constraints, and path following cost function, where x_t is the target path and x_actual is the current state of the vehicle. And the next slides denotes the algorithm that we use it for minimizing the error. Next slide. So here we denote how for each time step, we try to calculate the actual error between the desired and the target and the actual variable and try to minimize that. Next slide. Now here we have our MPC demo.
Hey everyone, so here's our spline generation for MPC demo. So first thing I'm doing here is running Carla. That's our simulator. And we're also running RViz, which is our visualizer tool for any data that's being passed through ROS. The next thing we do is run our environment model as well as our get behavioral service, which we will need for generating our splines. And this is our spline generation node that's currently being run in this terminal here. And pretty much it's just doing a service call to the get behavioral service, and using the data that it's getting back, it's generating a quintic parameter spline. And that's being published to this particular topic. And the MPC controller will be reading that topic or subscribe to that topic. So it'll be reading that data or or the splines that are being generated. So let me just show you what that topic looks like. So this is the live data that's being published. It's the spline that's being published via this topic. So we have our A values, and we also have our B values right here. So here is the output for the MPC controller, and this is the MPC node. Again, you can see that it's subscribed to the spline as well as some odometry as well. And it's using these two things. It's generating X, Y coordinates as well as speed and steer for the vehicle. And so let me just show you this output coming off of the MPC controller, and it's under the topic called MPC predicted output. So so here's our X, Y coordinates and our angle for the steer, as well as our forward speed. And the other thing you can also see is our act path parameter. And this is pretty much can be a value between 0 and 1. And it represents a percentage of how much of the spline you have traveled. And so we are currently at the 24% stage. Now, as we're moving and we're continuously generating splines, these splines are always being replaced by newer ones. And so this value doesn't really go up until you have reached your destination. And when you have reached your destination, it'll start to go up to 1, at which point, when it reaches 1, you will have arrived at your destination. So that's the way this works. Now, let me just explain what's going on here. We have our yellow line, which is our reference line, our Frenet reference, as well as this pink line, that's the MPC predicted output. And so the RViz tool is pretty much gathering the MPC outputs that it's getting, and it is showing this in the pink line as to what the MPC controller thinks we should be doing. So obviously, you can see here that it's a work in progress. We still have some work to do in terms of tuning this MPC controller so that it fits closer to the reference.
Cool. And to finish up.
Hey everyone. So
some of our ongoing work, including building the
so here's our spline generation.
Including building an MPC Carter bridge for passing in MPC output to the Eagle vehicle, as well as dynamic obstacle avoidance. And some of our future work includes combining the strengths of front-end maneuver planner as well as MPC controller. So as Ayush mentioned earlier, right now we're taking in the pass from the front-end planner and passing into MPC. And in the future, we hope to be able to get that pass from behavior directly. Thank you so much for the talk.
Thank you.
Yeah.
Hope you guys had fun.
Hope you guys enjoyed it.
Yeah, thanks, guys. That's a great talk. So I just want to, open up the floor to any questions. Like 15 minutes or so for questions. Sorry, could you actually go back to the slideshow?
Yeah, sure. Yeah, we'll just go to the one. Yeah, we're open for questions.
I actually had a question. So you mentioned you have that path parameter, right? So what's the it's sort of like an optional parameter, but what's the actual outcome? Like what's the visualizable outcome of using that path parameter versus not using that path parameter?
Kushan, that's a question for you.
Yeah, sure. So, the MPC output is only desired experience here that we pass out, but that add path parameter represents, it depicts that how close you are to a destination, and when your reference line again changes, that path again that path parameter again reverts back to 0 and goes towards 1. So it varies between 0 to 1 unless you reach your destination, your initial pose and the goal pose, current pose and the goal pose.
But why do you need it? Like, you should be able to estimate your position along the spline, right? Without it.
Yeah. So for now, we don't have that the exact distance, but we are working on it.
Okay, cool.
So I guess I kind of know the answer to this, but for everyone in the audience, what work are you guys doing, or like the team in general doing, for the like prerequisites? Like specifically, you gave some details about the feasibility checker of like the lane change maneuver. So yeah, how does that work within the stack?
That is a question for Ayush.
Well, the fees. So currently, since we're local planning, that is something we are currently working on. So right now, we only gather data from the behavioral planner, and then generate our splines from there. But yeah, I think there's just some more work to do in terms of determining when we need to do a lane change, and yeah, just gathering that data.
Right. So in case of an obstacle present in your path, a longitudinal distance needs to be calculated, and based on that, the sigmoid functions a parameter needs to change according to the urgency of the maneuver. And we are trying to get that parameter, get that longitudinal distance from the occupancy grid team.
Right. So how? So like you need the longitudinal distance, which like has some relation to A, right? And then you also need B. And then so we have this like, well, let's say like we have some values for A and B. We calculate Y, right? But then like we calculate Y for any X. it's a function, great. Like how does that actually influence the control actions output?
Okay, so to determine B, we have to find the kappa. Kappa is your curvature, and we have to find the maximum value of curvature, which is inverse of your radius, and that results in two methods. You either set B value to typical B lat LC to perform your lane change, or you use numerically generated data to fit a 2D function which maps the value of A and B to your kappa max and LC, and then you find the root of equation which comes out somewhere around 3.6 m, and you use that.
I don't know if other people understood that, but I could not understand that. Maybe it's a bit more complicated than we have the time to explain here. So I will follow up. But yeah, I do see that it will change the curvature, like the maximum curvature of the path of the vehicle. But yeah, I guess the details of how the curvature is calculated based on the sigmoid parameters, that's a bit complicated.
I have another question about this kind of action combined with the curvature of the road. So earlier you showed examples of generating splines that onto how the road curves, but I'm curious about how you combine this like control curve with the curvature of the road. Like, do you just sum it up, or is there other operations that you do?
Oh, yeah. For that, we do find Euclidean distance between the current point and the next point, and then based on that, we make calculations.
Yeah, so Stephen, it is addition, right? Because all of the functions are
it is.
parameterized over either longitudinal distance or time. Not sure, but when you add the two functions together, it'll work properly, since everything's like parameterized properly by longitudinal distance.
Yeah.
Oh, okay.
Sorry, what's longitudinal distance?
It's like the distance along the road. So you have longitudinal and lateral distance. So this is to avoid, so if you're going around a turn, using Euclidean distance won't be very good, because, the road moves. But if I just care about like the distance along the road, which is curvy, or the distance I am away from the road, which is curvy, the first being longitudinal distance, the second being lateral distance.
So it's kind of like not caring about like whether the road like turns or not.
Yeah, like you're ignoring the road geometry.
Okay, got it. I guess one question I have is like, why did we switch from like, because like you said last year we used Frenet planning. Like, why did we change to MPC?
I guess I can talk more about it, but I guess Ben from WATO is the right person you want to ask that question to. Ben is he here?
Don't think so.
Yeah. So we tried to integrate our Frenet planner with PID controller at first. So there was much noise when we were trying to calculate cross-stack error and trying to minimize the error. And we noticed some lateral deviations as well. So we switched to using feedback, your PID controller with the feed-forward controller. But again, we were facing problems there as well. And then I guess Charles implemented Stanley controller as well. Right, Charles?
Yeah. So I guess the short answer is the previous implementation is fast, but it was like not as performant in terms of like qualitative performance. But we're hoping that MPC will be smoother or more accurate.
Yeah, and the nice thing about the MPC approach as well as the title of this presentation, like it's simultaneous local planning and control. So the outputs of your planner are just direct control actions, whereas the output of the Frenet planner is a path, but then you need to implement another control layer underneath that path to actuate it. And so when you increase the number of different layers between your like global path and your actual control actions, it's just more opportunity for noise to creep into the system. So yeah, we really like the integrated local planning and control approach. Well, in theory, we like it. We'll see how it turns out for the competition.
We have a question from Mahir. Is there a reason for using multiple splines rather than just trying to follow the reference line from Behavioral Planner? Are the multiple splines used for MPC might be missing something?
Yeah, so pretty much the way MPC works is that we use splines. So basically, we look at what happened in the past and what is happening currently in the present state, and then we, depending on those splines, we try to predict a new spline. And so that's just the way MPC works. It works with multiple splines at a time, just to predict what's going to happen in the future, or what we want to do in the future.
So you internally store, is it like you internally store the previous defined control action and like use that to influence your next control action?
Right. So we would look at our previous spline and we would look at our current spline, or not our current spline, sorry. We would look at our previous spline and we would look at our current state of the vehicle, and then we would generate a new spline. And then that would be a continuous thing. Right, Prashant? Maybe you could explain more.
I have a question. Is there a reason to use, like, you have two different functions, one for like changing lanes and one for overtaking? Is there a reason why you can't like use two lane change maneuvers instead of the overtake function? Is there a benefit to the overtake function?
I think the overtake function is probably just more efficient in a way, because you know, if there's only one obstacle in front of you and you know there's some longitudinal distance in front of that obstacle, you can generate your overtake function based off of that instead of having to do a lane change and then figuring out how to do a lane change again. You're determining both of them at once, so it's more efficient.
Okay, that makes sense.
I guess what Anthony was trying to ask is that is there a way to make this make this behavior more generalized instead of having like one specialized function for each?
Currently, we are trying to do this. I think specifically, like in a specific way, like a lane change and a double lane change. I'm not aware of any way of making this a more generalized approach. Maybe Kushant could elaborate on that more.
Of course, we can do a more kind of generalized thing, but then we'll have to have a mapping of each state and action, and then implement something like a policy kind of thing, where looking at your action, you have some kind of a reward function, which gets, you pay a certain reward or penalty based on that action. And you generalize it for all the state and actions. Something like maybe Q learning or reinforcement learning, I would say. But that would be more complex to implement.
Okay, I see. Yes, these policies are too complex to be defined by hand, eh?
Yeah.
Okay, cool. That is all the time we have today. Thank you everybody for coming, and thank you Kushant, Ayush, and Stephen for the amazing presentation. This is being recorded, so we'll post it somewhere. Yeah, thank you everybody for coming.
Thanks, Charles. See you guys all later.
Thanks, Charles.
Thanks, Charles.
Yeah, thanks everyone, and thanks, Charles.
Thanks, everyone.
Thanks.